Welcome to the deep dive. You know, when you look up at the night sky, the moon feels like, well, like the one constant thing up there, right?
Absolutely. It's our quiet, watchful companion. Seems like it's always been there, exactly as it is.
But here's the twist. What if I told you that steady companion is actually leaving? It's in the middle of this incredibly long goodbye.
It is. It's slowly, but yeah, definitely drifting away from Earth.
It sounds so strange, like counterintuitive.
It really does, doesn't it? Because
Right.
we see it as this anchor. But the universe is always changing, even if it's super slow sometimes.
So before we dive into why it's leaving, maybe we should talk about why it's even important that it's here. It's done a lot for Earth, hasn't it?
Oh, absolutely fundamental. Over, what, 4.5 billion years, his role has been monumental?
Monumental how? I mean, beyond looking nice and, giving poets something to write about.
Well, think of it like a giant gyroscope for Earth. It steadies us.
A gyroscope.
Yeah, it reduces the wobble on Earth's axis. That stabilization gives us a much more, well, stable climate. Less extreme temperature swings, probably crucial for life developing the way it did.
Okay, that's huge.
And then there are the tides, of course. It's gravity pulling on the oceans that's literally shaped coastlines, influenced navigation, whole civilizations, really.
Right, the tides. Can't forget those. So it's not just some rock up there.
Not at all. It's a vital part of the Earth system.
Okay, so this vital, constant companion is drifting away. Why? How does gravity not just, hold it in place?
Ah, see, that's where the physics gets really cool and kind of weird. It's not being pushed.
No.
No, it's actually being pulled away. Pulled by the very tides it creates on Earth.
Pulled by the tides. How does that work?
It's this subtle sort of cosmic dance, an energy exchange.
Yeah.
And that's what we're going to unpack in this deep dive. The exact physics, where the energy comes from, how fast it's happening.
And what it all means long term
Yeah.
for Earth's past and its future.
Exactly. The whole story of this long goodbye.
Okay, so you said the tides pull it away. I get that the moon's gravity causes the tides, the bulges in the ocean.
Right, that's step one. The moon pulls on Earth's water, creating those bulges on opposite sides of the planet.
Yeah.
But here's the key bit. Earth spins on its axis way faster than the moon orbits around us.
Okay, much faster.
So as Earth rotates, there's friction, right, between the ocean floor and the water. And that friction drags those big, watery tidal bulges slightly ahead of the moon's position in the sky.
Ahead. So the highest tide isn't directly under the moon, it's a little bit in front.
Precisely. That slight offset, that bulge of water being slightly ahead, is everything.
How can a little offset do that much?
Because that forward bulge has immense mass. Water is heavy, and its gravity pulls on the moon. It's like a gentle but constant gravitational tug forward on the moon, giving it a tiny, tiny speed boost in its orbit.
A speed boost, so it goes faster.
Well, here's the counterintuitive part about orbits. When you give something in orbit a boost like that, it doesn't just speed up in the same circle.
No?
No, that extra energy actually pushes it into a higher orbit, a wider, more distant path around the Earth.
And the tides are literally flinging the moon further away, bit by bit.
Day after day, year after year. That's exactly what's happening. The moon creates the force that pushes itself away.
That's wild. But, okay, Physics 101. Energy can't be created or destroyed, right? Where's the energy for this boost coming from? There has to be a cost.
There is. And Earth pays the price.
How?
This whole interaction acts like a brake on Earth's rotation. The energy to accelerate the moon, to push it higher, it's stolen directly from Earth's rotational energy, our spin.
So, wait. As the moon drifts away, Earth is slowing down?
Yep. Our days are getting longer.
Longer. By how much? Is it noticeable?
Oh, infinitesimally.
Yeah,
We're talking microseconds per year, maybe. Nothing you'd ever perceive in a lifetime. But it's measurable.
Wow. A tiny daily price for the tides. So, okay, this is happening. How fast is the moon actually drifting? Can we measure that?
We absolutely can. And with amazing precision, actually. Using lasers bounced off reflectors left on the moon by the Apollo missions.
Lasers. Cool. What do they show?
They show the moon is moving away at about 3.8 centimeters per year.
3.8 centimeter. That's like how fast your fingernails grow.
Pretty much exactly, yeah. That's why we call it the long goodbye. It's incredibly slow on human timescales.
But over billions of years, 3.8 centimeters a year must add up to a huge distance.
It adds up massively. It confirms what scientists figured out from the physics. The moon must have been much, much closer in the distant past.
How much closer?
Calculations suggest maybe 250,000 kilometers closer, perhaps even more.
Whoa! Imagine looking up then, the moon would have looked huge.
Absolutely colossal in the sky.
Yeah.
Many times larger than it appears to us now. a truly dominating presence.
That's almost hard to even picture, just overwhelming. Okay, so this slow drift,
Yeah.
where does it end? Does the moon just keep going forever until it, like, leaves us completely?
Well, if you just run the simulations based on this interaction alone, it suggests the moon would eventually stop receding, maybe in about 15 billion years or so.
It'll reach a stable point.
15 billion years. Okay, so it doesn't leave entirely in that
Oh,
scenario.
there's a bigger clock ticking in our solar system.
Oh, what's that?
Our sun. It's not going to stay as it is forever. In about, say, 6 to 7 billion years, it's going to start dying. It'll swell up into a red giant star.
A red giant, I've heard of that. Big and red.
And engulfing. That expansion is predicted to swallow Mercury, Venus, and very likely Earth as well.
So Earth gets engulfed by the sun, which means the moon too.
Yeah, it puts a rather definitive end to the moon's recession, doesn't it? And Earth's everything else, a shared fate.
Wow. So, yeah, that puts a poignant cap on the longest goodbye. Kind of poetic almost. But just hypothetically, what if the moon somehow got far enough away before the sun expands? Could it escape?
It's unlikely given the timelines, but if it did break free from Earth's gravity, it wouldn't just float off into space.
Wow. No, it would then be primarily influenced by the sun's much stronger gravity. It would likely fall towards the sun.
And then?
It would be captured and, well, vaporized. So even in that unlikely escape scenario, it still meets its end via the sun. The destiny seems pretty intertwined.
It's amazing to think this whole process, this 3.8 centimeters a year, is happening right now. Even though we can't feel it, it's constantly reshaping our planet's relationship with the moon on these huge timescales.
It really underscores that we live on a dynamic planet in a dynamic system. Nothing is truly fixed, even something as seemingly permanent as the moon in our sky. It's all part of a slow cosmic dance.
It's a constant state of change.
Exactly. Even our closest celestial neighbor is on this long journey away from us.
A goodbye spanning billions of years. It really is the longest goodbye. It's beautiful, I guess, but also a little bit sad, you know?
It is. It gives you a different perspective.
Definitely. So maybe next time you look up at the moon, don't just see it as that constant, unchanging thing. See it as, well, a participant in this slow, gradual transformation, this cosmic dance.
Yeah. And maybe ask yourself, what does this incredibly long goodbye tell us about change itself, about permanence, and maybe about our own small place in this vast, always evolving universe?
That is definitely something to think about. Until next time.